Hi everyone, so this is Dr. G. Ravindranath Reddy working as Assistant Professor in MLR Institute of Technology, Hyderabad. So we are discussing numerical methods and integral transform course. In that we are at the Laplace transforms. Now in this video we will see what is definition of Laplace transform and we'll find out Laplace transform of some elementary functions here. In the previous videos we have seen the introduction where you can use the Laplace transforms in our engineering. So in this we will define the Laplace transform, then we will go for the Laplace transforms of elementary functions here. So when you come to this definition of Laplace transform, so I have taken a function f of t. So the function is in terms of t, and the function is defined for all the positive values of t. So then Laplace transform of f of t is denoted by L of f of t. That means Laplace transform of f of t is defined as, already in the previous video we said that this Laplace transform is depends upon this Laplace transform, we can also call it as integral transform. So if you want to convert this function f of t into a bar of s, we are applying the Laplace transform that is possible only by using this integration. So integral 0 to infinity e power minus st into f of t dt. So by using this integral we are transferring the function of t in terms of another function of s. This is the transformation done from variable t to variable s. So this Laplace transform L of f of t, whatever after applying the Laplace transform for the function f of t, after evaluating this integral, you will get the value, that integral value in terms of s. So that is represented with f bar of s. So here s is a parameter which is a real or complex number here. Now the symbol L, we can call it as a Laplace transform operator. So which transforms from f of t to f bar of s. So the simple definition for this Laplace transform is Laplace transform of f of t is equal to, so we can take integral 0 to infinity e power minus st into f of t dt. So once if you solve this integration, you will get a function in terms of s that we can consider as f bar of s. Now we'll take some elementary functions here. Now we'll see how to find out the Laplace transform for that elementary functions here. So here the first one is Laplace transform of k. Here k is a constant. Suppose whenever we want to find out the Laplace transform of 1, Laplace transform of 2, so whenever we want to find out the Laplace transform for constant values, then we can use this one. So Laplace transform of k is equal to k by s. We can keep positive values for k. K is equal to 1, 2, 3, 4 and 5 and so on. By giving some values for k, we will get the Laplace transform of that constant value. So now we will see how to prove this condition here. So take the definition of Laplace transform, just what we have studied now. So the L of f of t is equal to integral 0 to infinity e power minus st into f of t dt. So now I want to find out the Laplace transform of this k here. So in this definition, wherever we are having f of t, I want to replace that f of t with k. So you will get Laplace transform of k is equal to integral 0 to infinity e power minus st into, we are changing that f of t with k. So where k is a constant value, so we can take that constant outside this integration. So the remaining one you will get k into, the remaining function is e power minus st. Integral of e power minus st. Use that formula and find out that integral value. So you will get e power minus st by minus s, and then substitute the upper limit and lower limit 0 to infinity. So here if you substitute 0, so we are applying the integration with respect to t. So this s minus s becomes a constant. So you take that constant outside. Now here you will get e power minus, in place of t, replace t with infinity. So infinity into anything equal to infinity, you will get e power minus infinity minus e power, in place of t, substitute the lower limit 0, e power 0. So this is minus k by s. So e power minus infinity, we can consider that value is equal to 0. Minus e power 0 is 1. So 0 minus 1 you will get minus 1, minus of minus you will get k by s. So this is the way. So we got this value is equal to k by s here. So now the next one is Laplace transform of t. Suppose if you get f of t is equal to t, then you will get Laplace transform of t. Now how can you find out this Laplace transform of t? So that is Laplace transform of t has given us 1 by s square. Now we have to prove that Laplace transform of t is equal to 1 by s square here. Same, whatever the procedure we followed for the first one, follow the same procedure. Take the definition of Laplace transform, then replace f of t with t here. You will get Laplace transform of t is equal to integral 0 to infinity e power minus st into t into dt. Now here, so in the exponential function we are having a t variable, and here also we are having a 2 t variables. So here, if you want to evaluate this integration, we have to apply integral of uv formula. So now apply the integral of uv. So take the help of the word highlight and identify the function which one we have to consider as u and which one we have to consider as v. So exponential function t is an algebraic function. So t here a represents the algebraic and e represents the exponential function. Out of these two functions, here algebraic function comes first in that word. So we have to consider t is equal to u and the remaining exponential function as v. So now apply integral of uv formula here. So u into integral of v minus integral of u dash into integral of v whole d. So t into integral of v, that is integral of e power minus st. Just now we have seen integral of e power minus st is e power minus st by minus s minus integral of u dash. Our u is equal to t. Apply the derivative, you will get 1 into integral of v, that is whatever the value we got here, you take this value and then simplify and go for the one more integration here. So t into e power minus st by minus s minus 1 into this one, you will get this e power minus st integral of e power minus st. This can be written as e power minus st by minus s. Already in the denominator we are having one more minus s. So minus s into minus s, you will get minus s whole square. So now substitute the limits here. So after substituting the limits, upper limit and lower limit, finally you will get this value is equal to 1 by s square. So Laplace transform of t is equal to, we can consider this value is equal to 1 by s square. So next, suppose if we get Laplace transform of t square, Laplace transform of t cube and Laplace transform of t power 4 and so on, then if you want to find out the higher powers of that t, then we have to take the help of this Laplace transform of t power n which is given as n factorial by s power n plus 1. So this is n is a, so since here we are having a factorial, so we know that factorial is applicable only for the positive integers. So that's why we have taken n is a positive integer. Now we have to prove this condition. Laplace transform of t power n is equal to n factorial by s power n plus 1. So follow the same procedure, take the help of the definition of Laplace transform and then in place of f of t substitute f of t is equal to t power n. So here you will get integral 0 to infinity e power minus st into t power n dt. So e power minus st, this is one function in terms of t. T power n is also another function in terms of t. So here also we have to use the concept of integral of uv. So use that integral of uv. So t power n into integral of v e power minus st by minus s minus integral 0 to infinity derivative of t power n. So derivative of t power n is n into t power n minus 1. So this is the value of derivative of u, and integral of v, this is the integral of e power minus st. You write down this is e power minus st by minus s. So now in the first term, if you substitute the upper limit and lower limit here, if you substitute upper limit in the e power minus st, if you substitute t is equal to infinity, you will get e power minus infinity. We know that this value is equal to 0. So 0 into anything equal to 0. So this When we substitute the upper limit here, you will get 0 here. Now put the t is equal to 0. T in place of t, if you substitute t equal to 0, 0 power n, that is 0. 0 into anything equal to 0. So this whenever we substitute the upper limit and lower limit in this first term, then both upper limit value and lower limit value, this value becomes 0. So that's why we have taken this value is equal to 0, 0. And now keep, so you send this minus outside, it becomes plus. So here we are applying the integration with respect to t, so this n and this s becomes a constant, so you send that n by s outside, and the remaining one is integral 0 to infinity e power minus st into t power n minus 1. Now here this is equal to, so n by s, so by the definition of Laplace transform here, whenever we are having t power n, we have taken this integral as Laplace transform of t power n. But in place of t power n here we are having t power n minus 1. So this entire integral can be written as Laplace transform of t power n minus 1. So now if you want to complete this, once again we have to find out the Laplace transform of t power n minus 1. Whatever the value we get, once again we have to substitute that value in the equation 1. Now we will see how to find out the Laplace transform of t power n minus 1. Follow the same procedure here. Use the definition. In that replace t equal to t power f of t with t power n minus 1. Follow the same procedure. Apply the integration by using uv formula. So finally here you will get that Laplace transform of t power n minus 1 is equal to n minus 1 by s into Laplace transform of t power n minus 2. So once if you observe this equation 1 clearly, so if you find out the Laplace transform of t power n, the power of t is n, so here we got n by s, and the lowest next value is we have to consider as t power n minus 1. And similarly t power n minus 1, the power of t is n minus 1, so we have taken n minus 1 by s into the previous value of n minus 1 is n minus 2. So next follow the same procedure here. Whatever the value we got, you substitute this value. So similarly if you go for the Laplace transform of t power n, follow the same procedure, you will get n minus 2 by s into Laplace transform of t power n minus 3. So if you go on applying the Laplace transform here repeatedly, we can get Laplace transform of t power n is equal to, so here in place of this I have substituted this value, that is n minus 1 by s, so this becomes n minus 1 by s, and in place of this Laplace transform of t power n minus 2 I have substituted this value n minus 2 by s. Once again you will get Laplace transform of t power n minus 3. So in place of this we can substitute n minus 3 by s. So like this if you repeat this process until n number of times, finally you will get Laplace transform of t power n minus n. So Laplace transform of t power n minus 1, n minus n, you will get t power 0. T power 0 is equal to 1. So we can take Laplace transform of 1 here, n into n minus 1 into n minus 2 into n minus 3 into 3 to 1. So this entire numerator we can consider as the factorial, n factorial, and here if you multiply the number of s here, 1 s into s square into s cube. So if you multiply n number of s here, you will get s power n into the remaining one is Laplace transform of 1. So Laplace transform of 1, so we have proved in the previous slide, we have taken Laplace transform of k is equal to k by s. You put k is equal to 1 here, so you will get Laplace transform of 1 is equal to 1 by s. So if you substitute here 1 by s, so n factorial by s power n plus n into 1 by s. So s power n into s, you will get n factorial by s power, bases are equal, so you must add the powers. If you add the powers, you will get s power n plus 1. So this is our Laplace transform of t power n is equal to n factorial by s power n plus 1. So this formula is used whenever we want to find out the Laplace transform of t cube, Laplace transform of t power 4, Laplace transform of t power 5. So only 3, 4, 5 or all these are positive terms, positive integers, so we can find out the factorial value. Suppose whenever we want to find out the Laplace transform of 3 by 2, so then if you use this formula, then it is not possible to find out 3 by 2 factorial here. But even that n value is a positive value, so whenever that positive value in the if you get that value in the fractions, then this formula is not applicable. So if n value is in the form of p by q, then this n factorial by s power n plus 1 is not applicable here. So for that we have to go for the another formula. So by taking the help of gamma function, we are going to find out the Laplace transform of t power 3 by 2, Laplace transform of t power 1 by 2, Laplace transform of t power 5 by 2. So whenever the power of t is not a integer, then we can use that. Instead of taking n factorial, we can convert that n factorial in terms of gamma function here. So we have the relation gamma of n plus 1 is equal to n factorial. So n is a positive integer. So now we are having n factorial, so I want to replace that n factorial with gamma. So gamma of n plus 1 by s power n plus 1 here, because gamma of n plus 1 is equal to n factorial. By taking the help of this gamma function, we can convert this n factorial in terms of gamma of n plus 1. Now by using this, we can find out the Laplace transform of 3 power 3 by 2, Laplace transform of t power 5 by 2, Laplace transform of t power something 7 by 2. Like this we can find out this value here. So this is the formula of gamma function. So gamma n is given by integral 0 to infinity e power minus x into x power n minus 1 into dx. So by using this, we can find out that gamma function value. So here we are having some properties of gamma function. Gamma of n plus 1 is equal to n into gamma of n, and gamma of n plus 1 equal to, we can take that n factorial, and gamma of 1 is equal to 1, gamma of pi by 2 is equal to root pi, and similarly we are having gamma of minus 1 by 2 is equal to minus 2 root pi. So now we can use this formula whenever we want to find out this Laplace transform of t power 3 by 2. That 3 by 2 is a positive value but not an integer. So whenever we are having n value is greater than 0, we can use this standard formula, Laplace transform of t power n value in terms of gamma function. Now let us go for the next one. Laplace transform of e power at is equal to 1 by s minus a. So now we will see how to find out the Laplace transform for this exponential function here. So for all these Laplace transform of these elementary functions, we have to take the help of this Laplace transform definition. So take the Laplace transform definition and replace that f of t with exponential function e power at. So already in this integral we are having one exponential function e power minus st, and here we are taking one more f of t, that is exponential function e power at. So bases are equal, so we must add the powers. So now by adding this, you will get e power minus of s minus a into t into d. Use this e power minus a integral of e power minus ax into dx. Use this formula, find out that integral value, substitute that limits, upper limit and lower limit, then we can get our required value, which is equal to 1 by s minus a. So finally we can conclude Laplace transform of this exponential function, Laplace transform of e power at is equal to 1 by s minus a. So whenever we are having a positive power for this exponential function, here you will get a negative sign. And similarly, if you have a negative power for this exponential function like Laplace transform of e power minus at, so you will get the same formula, but in place of minus, here we have to keep plus. So here if you have a negative power, here we have to keep positive sign. If you have a positive power, here we have to keep negative sign here. the remaining one is same. So this is Laplace transform of e power minus at is equal to 1 by s plus a. So next we will take this next formula. So Laplace transform of cos h at. So this is a hyperbolic function cos. Now for this hyperbolic function we will see how to prove that condition Laplace transform value is equal to s by s square minus a square. So now just now we have seen the Laplace transform of e power at and Laplace transform of e power minus at. So first I want to express that hyperbolic function in terms of exponential functions. So cos h at we can write it as e power at plus e power minus at by 2. This is the relationship between hyperbolic for cos and exponential function. Now apply the linearity property, that is 1 by 2 is a constant, so we can take that constant outside that Laplace transform. So now apply the Laplace transform of e power at, Laplace transform of first term plus Laplace transform of second term. So the first term is e power at, so Laplace transform of e power at plus Laplace transform of e power minus at. Just now we have derived some formulas for Laplace transform of e power at. So that is 1 by s minus a, and the Laplace transform of e power minus at we have derived 1 by s plus a. Now take the LCM for this, s minus a into s plus a. So you will get s square plus s square minus a square. So now this a and this a gets cancelled. You will get 2s by 2 into s square minus this 2 gets cancelled. Finally you will get s by s square minus a square. So that is the RHS value here. So if you want to find out the Laplace transform of hyperbolic function cos, then you convert that cos in terms of exponential functions. Then apply the Laplace transform of e power at and Laplace transform of e power minus at. Then simplify by taking the LCM. Then we can get our required value here. And similarly, we will take another hyperbolic function sin h at. So take this same as usual what we discussed in the previous proof. Sin h at, express that sin h at in terms of exponential function, because we know the Laplace transform of e power at and Laplace transform of e power minus at. So separately take this Laplace transform. So Laplace transform of e power at and Laplace transform of e power minus at, write down. Then take the LCM. You will get the denominator as s square minus a square, and this s and this s gets cancelled here. So 2 gets cancelled. So finally you will get that value is equal to a by s square minus a square. So this is another formula for Laplace transform of sin h at. So now we will discuss one more thing, that is Laplace transform of cos at and the Laplace transform of sin at. So here in the lower classes we have seen Laplace transform of I theta e power I theta is equal to cos theta plus I sin theta. Now take the help of this, because we know the Laplace transform of exponential function. So we can take e power I at is equal to cos at plus I sin at. Now apply the Laplace transform on both sides here. So Laplace transform of cos at plus I sin at is equal to Laplace transform of e power I at. So this is of the form Laplace transform of e power at. So this can be written as 1 by s minus a. So here a is ai, so 1 by s minus ai. Now rationalize this denominator, you will get s plus ai by s plus ai. So this can be written as s plus ai by, this is a minus b into a plus b. So a minus b into a plus b can be written as a square minus b square. So ai whole square. So this can be written as s plus ai by s square plus I square, that is minus, already here we are having minus, so minus of minus plus a square. So now you can take this s sub by s square plus a square plus I into a by s square plus a square. So now this is equal to Laplace transform of cos 80 plus I is a constant, so we can take that I outside. Laplace transform of sin 80. Now equate the real and imaginary parts here. So you will get Laplace transform of cos 80. Take the real part in this at RHS side. This is our real part, so we can take s sub by s square plus a square. And if you compare the imaginary part here, you will get Laplace transform of sin 80. So on the RHS side, this is our imaginary part, so we can take a by s square plus a square. So Laplace transform of cos 80 is equal to s by s square plus a square. Laplace transform of sin 80 is equal to s by s square plus a square. So these are the elementary functions of Laplace transform. So now in this video we have discussed the Laplace transform of some elementary functions here. So now in the next video we will go for the first shifting property of Laplace transform. So when we can apply this first shifting property of Laplace transform, and we will take some problems in the next video. Thank you.